In this video we're going to consider how we can use matrix algebra to solve systems of equations. So these are really simultaneous solutions where we've got multiple equations in multiple variables. And we're going to start off with, or basically actually we're going to pretty much only at this stage do simple, two equations in two unknowns. But the time when this becomes really powerful is when we have large systems of equations. So just as an example, let's say we were trying to solve the following system simultaneously. So let's go 4x minus y is negative 11 and negative 5x minus 3y equals positive 1. So we're going to find the simultaneous solution to that. Now obviously algebraically we could just do that using elimination or substitution, and that wouldn't be a very difficult process. When we solve or when we do algebra with matrices, we're going to work very similarly to how we would doing algebra with scalars. So let's just think, for example, if I, over here I'll just write down, if I had the equation 3x minus 5 equals, 12, something like that. Okay, then I would think to myself, well, first of all, I'd add the 5 to both sides, so I'd say 3x equals 17. Now, at this step here, where I'm trying to do the product of the scalar that I know and the scalar that I don't know, x, to get 17, I say to myself, well, just do the opposite of multiplying by 3, which is dividing by 3. Or alternatively, so that we can think about it with matrices, we'd say multiply by the inverse of 3 on both sides. And that's in fact how we'd solve it. We'd end up with then just x is equal to 17 over 3. So we're just multiplying by the inverse of 1 over 3, and that's going to get us the solution there. Now, one thing to note here, and I'll come back to this at the end, but when I'm dealing with scalars, because scalar multiplication is commutative, it doesn't matter where I do the 1/3, the multiply by 1/3. So it would have been exactly the same to say 3x times 1/3 equals 17 times 1/3, or even to say 1/3 times 3x equals 17 times 1/3. So in other words, it doesn't sort of matter whether I multiply at the start or at the end of each side of the equation by 1/3. But with matrices, because matrix multiplication is not commutative, it is going to matter. All right, now I'm going to write this here in matrix form, and that means I could write it as the matrix 4, negative 1, negative 5, negative 3. So the coefficients there of x and y times xy equals the result here. Now if you need to just take a moment to convince yourself that that's true, all you need to do on the left hand side is actually multiply, row by column, and that first one is going to give you 4x minus y, so that's going to be equal to negative 11, and then multiply the second row times that column and you'll get negative 5x minus 3y, and that will equal the 1 in the matrix on the other side. So basically we can write that, or those two equations, as just a product, or in matrix form as a product of two matrices equals another matrix. Now if we then were to let or consider this as the matrix, let's say consider this as A times x equals B. Okay, so I've got a matrix A, which is all those coefficients, times a matrix X, which is my two unknowns, and that equals my matrix B. So what I'm going to say here, this is now very much like this line over here. Okay, I've got two sort of knowns and one unknown. I'm trying to find the unknown. So what I would say is, if I multiply here by the inverse of A, So A inverse times A, just like I did over on this side, I multiplied 3 by 1/3. And the reason for doing that was actually to get the identity, which was 1, because I just wanted 1 times x. So doing it with matrices, A inverse times A is going to give me the identity. So on this side, I'm just going to have I times x. And obviously, if I've done that on the left-hand side of the equation, I need to also do it on the right-hand side of the equation. So I did A inverse A times x, so I need to do A inverse B. So I've still got A inverse B over here. And then the identity times x, well, the identity times anything is just equal to itself. So I times x is just x, in the same way over this side as 1 times x is just x. That's the whole reason for multiplying by the inverse, is to get the identity and therefore just have x by itself. Alright, now these steps here, we obviously don't need to show that every time we're doing our working out. But I've put them in there so that hopefully then the next thing makes sense, which is to say, therefore, x, y is going to be equal to the inverse of 4, negative 1, negative 5, negative 3. So the inverse of that times negative 11, 1. So let's then keep going with that and say, well, the inverse of that is 1 over 4 times negative 3 is negative 12 minus 5. Then switch these around, so negative 3 goes there, 4 down there, the negative 1 becomes a 1, the negative 5 becomes a 5, times negative 11, 1. So all of that is equal to, what's that, negative 1 on 17. Negative 11, 1. Now here's a little strategy which will help you greatly in a lot of cases. Leave the scalar, the negative 1 on 17, out the front. Do the matrix multiplication first, because we can do that. Doesn't matter whether we do the matrix multiplication first or the scalar one. So let's multiply these two matrices together. Negative 3 times negative 11 is positive 33, plus 1 times 1 is 1. 5 times negative 11 is negative 55 plus 4. So what's that equal to? Negative 1 on 17. And this matrix is 34, negative 51. And now I can multiply the negative 1 on 17 into the brackets there. And both of these are multiples of 17, so that becomes negative 2. And positive 3. So we've done all our working. Let's write the left-hand side in again down here. Done all our working to get the result that x and y are equal respectively to negative 2 and 3. And of course we could do a quick check. Maybe take the first equation, say 4 times negative 2 minus 3. What's that equal to? Negative 8 minus 3 equals negative 11. So that certainly gives us the right result there. So our result is x equals negative 2 and y equals 3. Now I did just say right at the end that I would come back and talk again about the whole idea of commutativity. So because it was a times x equals b, and I had to multiply by A inverse here at the start, or left multiply by A inverse, because I need A inverse and A next to each other so that I can multiply them together to get I. So in this situation I couldn't put A inverse there, because then I wouldn't be multiplying A inverse by A. I'd be doing A times x first and then times A inverse. So A inverse needs to go directly beside A, and because I pre-multiplied or left multiplied by A inverse on the left-hand side of the equation, I must do the same on the right-hand side. So I can't sort of do it on the left on this side of the equation and then go and do it on the right on that side of the equation. Now if I had an equation like this, x times A equals B, well then I would need to do what's called post-multiplying. So to get the A inverse next to the A, I'd need it there, and therefore I'd need to do the same thing on this side of the equation. But most of the time when we're dealing with solving systems of equations, we're always going to be dealing with that one there, where it's A times X. Alright, so there's a way of solving systems of equations with matrices. Useful with 2x2s, not overly powerful with 2x2s, but definitely very powerful once we start getting much larger systems of equations.